Okay, so I've labelled all the forces on this diagram then, right? So I've got the weights here of A and B, tension and strain. Now, the tensions are equal throughout the string because it's a sort of smooth pulley here, okay? And it's a rough surface, so when it's released, it's going to accelerate this way, yeah? So the object A is going to be dragged across the table via this tension in this string. So there's obviously friction I'm going to be posing it, and we've got there the coefficient of friction, which is 0.3. So it says initially the system is at rest, but then it's released. So we've got to find the magnitude of the acceleration at A and the tension in the string. So what I'm going to do, I'm going to resolve in two places, okay? So if we consider, for instance, A to start with, okay, so resolving at A, okay. So if we resolve horizontally, so we're going to apply Newton's second law in the direction of motion of the string. So of course it's going that way. So remember Newton's second law, it says that resultant force, okay, equals to the mass times acceleration. Okay, so the resultant force in this case, well, you've got the tension pulling object A forward, but then you've got friction resisting it. So that's the resultant force, and that will equal to then the mass times the acceleration. We know the mass is 4 kilograms and the acceleration then is A. Alright, so then if we sort of resolve vertically, okay, now vertically there's no movement, isn't there? Okay, there's absolutely no movement at all. So we've got a balance there, we've got an equilibrium there. Okay, so vertically it's in equilibrium. So when you apply Newton's second law there, well, the resultant force is 0, isn't it? In other words, this take away this is 0, or quite simply we can say R is equal to 4G because they balanced. Okay. Now we also know a formula for friction, don't we? Okay, formula for friction. So we can say, look, since system is in motion, okay, friction is at its max. Okay. In other words, friction is fighting as hard as it can, so friction is equal to mu r. Okay. Now we know mu is 0.3. Okay, because it tells us in the question there, and of course then we know r is 4g. Okay. So we can actually work that out, can't we? 0.3 times 4 times 9.8. So I get 11.76. Okay. So what I can do then is I can sub it back in there. So therefore, T minus 11.76 equals 4A. Now if we apply then Newton's second law at B, okay, now in the direction of motion, well, we can see here then it's going this way, so 6G, the weight, is pulling it down, okay. Of course, you've got the tension in the string keeping it up, opposing it, so you've got 6G minus T equals to then mass times acceleration. So the mass is 6, acceleration there, okay. So then I want you to see then you've got two equations, 1 and 2, and we can add 1 and 2. Okay, we can always add these in this particular case, and what will happen then is that you'll notice, because we're solving them simultaneously, yeah, but you'll notice the tensions will cancel when I add them. So I've got T minus 11.76, add then this, well the T's will cancel, so I've got minus 11.76 plus 6G, and then add it together, which will be 10A. Okay, so then we get, well, we've got G to be 9.8, of course. So from there then, if I work that out on my calculator, minus 11.76 plus 6 times 9.8, so that is then divided all by 10, so I get 4.704 meters per second squared. Okay, to get T then, all you've got to do is sub that then into 1. So T minus 11.76 is 4 times then my answer. So I do that, I get 30.576 newtons.